in this diagram, phasor diagram, if you look at here, you can see that along the axis X, we have drawn the temperature, okay? And along the axis Y, we have drawn the pressure, but this phase diagram is only for water, okay? Different substance has different, this kind of diagram, phasor diagram. So here, pressure is along the y-axis and temperature is along the axis X. So for example, just consider one particular point over here. If you consider this point, if you increase the pressure, what will happen? It will convert it to, it will be converted to the liquid. So this phase is going to be liquid, okay? So below this diagram, if you are decreasing the pressure, what will happen? At the given temperature, if you decrease the pressure, what will happen? It will be in the gaseous state or in the state of vapor, okay? So this line you see here, basically the coexistence of liquid and the liquid and the vapor state, okay? This, if you consider this line over here, in this part, at a given, if you consider any particular point, then this side, effect of pressure, indicates that this side will be the solid phase, will coexist, and that other side will be the liquid phase coexist, okay? So, and in this other curve, you see here, I use the different color, and this is the sublimation curve. So this side will be the solid, and this side will be the vapor, okay? So this will say you, tells you how pressure will affect the change of phase, how it could change, okay? So if we are going to produce back all these curve, so like melting curve, boiling curve, and sublimation curve, they could meet at a particular point. This is called the triple point. So triple point is a particular point where all phase coexist. So this means at the triple point, all phases coexist. Beside that, only two phases, either solid liquid phase coexist, or solid vapor phase will coexist, or liquid vapor phase will coexist. So at this particular point, all the phases will basically coexist. Okay, so this is called the triple point. And this kind of diagram, where we call the phasor diagram, is basically the diagram of pressure and temperature. We call it the phasor diagram. Okay, so the video link below will also help you to understand this concept better. So these are the examples how like sublimations from solid to vapor will happen. Okay, you can read through this. And similarly, equilibrium between liquid and gas as two different boiling points inside a closed container, first container and second container, they will give you the explanation how the pressure affects those points, okay, those equilibriums. This is again the example of the condensations. So energy is released when water condenses, spreading the melting of ice in the glass. Let's go to the topic of heat transfer. Okay, so heat transfer we can understand in that way that heat transfer could happen in three different ways. One is the conduction, convection, and radiation. So in first mode, we call it the conduction. So heat transfer between two objects happen from point to point. So for example, say this is atoms, okay? This is another atom like this. If you give heat to this side, this heat is transferred to the second one. Then this heat is transferred to third one. Keep going like this. So this finally the heat will transfer from one end to other end. So this is the one end to the other end. But the particles will be in its own position. So particle will remain in its position. This means no motion of particles. No motion of medium, say for example. No motion of particles of medium. Okay. In the convection, it happens when energy transfer happens, but the actual motion of the particles. Okay. So for example, if you heat a water in a container, what will happen? The particle of water which are close in contact will got heat and it will move to upwards. Okay, and the cold water will comes down and it gets heated again go up. So this kind of cycle will keep running till the water gets heated. Okay, all the parts of the water gets heated. So in conventions, what will happen? There is a motion of particles of the medium. Okay, in other way we are getting heat is the radiation. In radiation happens, we don't need no need of medium. For example, we are getting the sunlight. Basically, we also get the sunlight and heat energy with it, but there is a vast space. There is no medium. So in the electromagnetic spectrum, from where we get the heat energy, we get heat energy by the mode is called the radiation. So in this mode, no medium is required to transfer the heat from one point to the other point. Okay. Let's start with the conduction. In conduction, say one side has high temperature TH and other side has low temperature TC. And the distance between the two objects is say D. Then heat will flow from high temperature to the temperature is called the low temperature. Let's see what equation or how this happens, right? So if hot object is at higher temperature and lower object is at lower temperature, so just I'm drawing the simplified picture over here. So this is the uniform rod that you saw just before. So this side is at high temperature end, this is at low temperature end. Okay, so for example, you can put this side to the heater, join to the heater. This other side you can put in the ice. So what is TH? TH is the temperature of one phase. Okay, and TC is the temperature of another phase. Okay, so TH is greater than TC. Okay, so you can write, so A is the cross-sectional area. Okay, this side, this phase. We can assume this L is the length. L is the distance between two phases. The same as the length of the rod. Distance between two phases. Okay. If this is the case, then you know that heat flows from higher temperature to lower temperature. Okay, so in this case, the rate of heat flow will happen from this phase to that phase. So heat flow will happen from left to right. Okay, so the rate of heat flow dq over dt, this is the rate of heat flow, will be equal to k times A times change in temperature delta T over L. Okay, so here this dq over dt is the rate of heat flow. Means heat flow in 1 second. Okay, K is a constant for a given material. It's called the thermal conductivity. Okay, of the material. So for iron, K value is different. For steel, K value is different. And each material will have a different K value. Okay, so this equation can be used to find the rate of heat flow in the conduction, because heat conduction happen, heat flow happens because of the phenomenon is called the conductions. Okay, so you can check the unit of K will be joule energy per second is watt per meter squared, and you can see per degree Celsius or per Kelvin, and basically this will cancel out, so it will be meter. Okay, so you can see, yeah, so watt per meter per degree Celsius or per Kelvin is the unit of the value K. Okay, so K value is different for different materials. So you can try this problem. So in this problem, they give you that the house wall is 13 centimeter thick, and other informations they give you like surface area of the wall. Okay, they give you inside temperature, they give you outside temperature, they give you the thermal conductivity. Okay, then you can find rate of heat conduction through house walls. Okay, and second question is how many 1 kilowatt room heater would be required to balance the heat transfers due to conduction. So you can try this problem based on the equation that you just saw. Okay, the other way the heat transfer will happen is, we just know, by the radiation, or we also call it this is related to heat, so we call it thermal radiation. So rate at which heat is transferred by an object via the radiation depends upon its temperature and surface. So for example, a rate of heat loss or gain will be equal to sigma times emissivity, surface area, and temperature power 4. But be careful that this temperature should be in Kelvin, not in Celsius or in other unit. Okay, must be in Kelvin scale. So Q by T means rate of heat gain or heat lost will be equal to sigma. It is a constant. It's called sigma. Is called the Stevens-Boltzmann constant. Stefan's Boltzmann constant, and this equation Q over T, E sigma times E, A times A4 is called the Stefan's Boltzmann law. Okay, so this just I want to say about that. Say, for example, this is the situation. Say you have this object, you hang in a ceiling. Okay, so its surface area is A. Okay, say it is a temperature of, say, for example, 500 Kelvin. This object, I just put some thing. Okay, if the outside temperature, say this is the room where you kept this ball, this hot ball in a room. So you can assume, say, room, and room temperature is, say, for example, it will not happen, say it is 0 Kelvin. It's not possible. Okay, it's not possible. So you know that this higher temperature, this is low temperature. So this means this ball, this ball will lose heat. So this metallic ball will lose heat. Okay. So how much heat it will lose? It's given by the Stefan's Boltzmann law. So it says that heat lost per unit time will be equal to sigma, its value is always constant. E value is called emissivity, surface area, and T4. So everything is given, so you can calculate. This is the rate of heat loss. This will be the rate of heat loss. Okay, heat loss by ball. So in general, if it's not given, we assume E as a E is equal to 1 for perfectly black body. We'll come to this point. Perfectly black body. Okay. A is the surface area. We can come to the other situations, because you know that room temperature at 0 Kelvin is not possible in most of the scenario. Okay, so we have the same ball, we have the same temperature, but now room temperature is not 0 Kelvin. Say, for example, it's 300 Kelvin. Okay, so in that scenario, this ball will do two things. Ball will lose heat and gain heat. What does it mean? You might be saying that, how this is possible? Yes. A thermal equilibrium means they are giving and taking the heat same amount. But this is not the case of thermal equilibrium. The temperature of ball will slowly go down. So this means the ball will lose more and gain less. Okay. So find how much it will gain the heat. Gain the heat. So according to Stefan's Boltzmann, it will be sigma E A. Temperature is gaining. Gaining means it will be gaining heat from room temperature. So you have to put this temperature. Okay. So I will say it as a T2. Okay. T2 power 4. So how much actually it is losing? It's losing from this sphere. From it has the higher temperature 500, so sigma will not change, E will not change, area will not change. Now it has temperature T1 is 500, so it will have T1 power 4. So net rate of, in this case, rate of loss of heat you know that it is losing more. So this minus that. So sigma E A T1 power 4 minus sigma E A T2 power 4. So that's how Stephen's Boltzmann law talk about heat gain and heat loss when there is a case of radiation. So this here, it happens because of the radiation. Okay, it does not affect whether there is a medium or not. Okay, because medium has no role in the radiation. So we say that black body means, let's see the example. If we incident heat or light, it could absorb completely. Okay, in that scenario, in this case, it will absorb completely. In this case, absorb completely, then we say emissivity is equal to 1. Okay. Other scenario, we can see that if you incident the heat, some part get reflected, some part get absorbed. So in this scenario, you can see that it is not going to absorb everything. So E value is less than 1. Okay, so those substance which completely absorbs heat is called the black body. It's called the perfectly black body. Perfectly black body. Okay, so a black object is a good absorber and a good radiator of heat, whereas a white, clear, silver object is a poor absorber and a poor radiator. Okay, so black cloth, for example, is a good absorber, and at the same time, it is the good radiator of the heat. Okay, so at this point, I will solve one problem here. Say, based on this Stephen's Boltzmann law, let's see a sphere of radius 2 centimeter with a black surface. Black surface means in this case they don't give you the value of E, so we assume emissivity equals 1. Okay, the sphere of radius means say we have this room, same as before. We have this ball, they give you the radius. They give you radius means we can find the surface area. Surface area, it will be 4 pi r squared, okay? Because you know the radius. So this is the surface area. Different shape has different area. This is a sphere, so surface area will be 4 pi r squared, okay? And they don't give you the value of E, emissivity, so we consider this as a perfectly black body. So your E value is 1. Okay, is cooled and then suspended on a large evacuated enclosure which are maintained at 27 degrees Celsius. See the difference here. Here the room temperature is 27. This is the room temperature. For room, for this ball, it is at low temperature. You see, it is minus 73 degrees Celsius. So by looking at this picture, you can guess that the ball will gain the heat energy, net gain. Okay, so this means it will be giving less but absorbing more. Okay, this will give less but it will take more heat. So for example, it will take more heat from the room. Okay, so it will have net gain. So let's find net gain or loss. So if the rate change up in thermal energy of a sphere is this, so they give you gain, net gain Q over T is 1.84 8 joule per second. This means you know that joule per second is watt. 1.848 watt. Okay, they give you this thing over here. This is basically the net gain. Okay, so as before, you have to find two things: how much it gained and how much it lost. Okay, so we can find a rate of heat gained by sphere. If you use Stefan's Boltzmann law, this will be sigma E value is 1. Be careful, your temperature is gaining heat from the room. So room temperature is 27. So 27 you convert to Kelvin, so you have to add 273 power 4. Okay, so temperature must be in Kelvin in when you are using the Stefan's Boltzmann law. Okay, so this means it will be, oh, I forgot to write A. If you see the equations, Stefan's Boltzmann law, it has A also, sigma EAT4. Okay, so let's write like sigma A, so it is 300 power 4. This is the heat gained by the sphere. You need to find again how much will be the heat lost by the sphere. So rate of heat lost by sphere. Okay, so this will be again Stefan's Boltzmann law, sigma E is 1, area, now it is losing the heat. So its initial temperature is 73, we convert to in Kelvin, so 273 add, so power 4. So it will be sigma A 200 power 4. Okay, now you can find, based on that, you have how much heat gained and how much heat lost. So net rate of heat gain. Okay, so this will be how much it gained and how much it lost. Okay, so it will be sigma A 300 power 4, and it lose, so total is losing in minus, we are sigma A 200 power 4. Okay, so you can plug this value, you know already, this value is given, this value net rate of heat gain, they give you 1.8.48, so you can plug that number, 1.848. okay, then sigma value is given, the value of sigma is 5.65 10 power minus 8. This is what 8 watt per meter squared and Kelvin power 4. Okay, this is sigma. A value, let's find A value somewhere. Okay, so area, I will write some down. Area will be 4 pi r squared. This is a sphere, so 4 pi. Radius they give you 2 centimeters, so in meter 0.02 meter squared. So basically it will be 5.02 10 power negative 3 meter squared. So you can plug this value of K in the above part. Okay, so you can plug this. A is 5.02 10 negative minus 3 meter squared. So this is 300 power 4 minus 200 power 4. Okay, so once you plug this value, you can find the value of sigma, but that's why in this case this value is not given, so you can remove this. Otherwise you can find both sides equal. So we want to find this value sigma. So if you solve, you will find sigma equals 5.65 10 power 8 watt per meter square k power 4. Okay, this is your answer. So important take home message is this from this equation is this: if we have an object higher temperature, say you can say for example 600 degrees Celsius, if you live in atmosphere or in the room, it will cool down. So after some time its temperature will drop, means it is losing the heat. So losing the heat means we are talking about the net loss of heat. So in reality, this ball, if at higher temperature, it is doing two jobs together, giving the heat, and at the same time, you're also taking more heat. In this case, it is taking less heat if the outside temperature is low. Say, for example, room temperature is say 25 degrees Celsius. This is room temperature. Okay, so this is the temperature. This is the temperature of ball. So it will lose more heat. Okay. Then gain. This is the lose part, losing, and this is the gaining part. So it will gain less and lose heat, but it will not meaning that it is always losing, it's gaining also. Okay, so this will happen in this kind of radiation. So it depends, either it is losing the heat or gaining the heat. So in this case, it will gain less and give more heat. So these are the examples. So for example, if you burn up a fireplace here, you are sitting in the sofa, you are getting heat by the radiation. You're also getting heat, room get warmed by convection, because the particle of air, it will transfer heat. And a small conduction. Conduction means there is if furnace is placed over some object, it also gets somehow heated. Okay, this is the example. And the another example, how this insulation helps us to maintain the temperature. You can find tons of example of conduction, convection, radiation, and this is the further resources. If you want to know more, this marked red one is more important for me to understand the concepts. You can also watch the other resources. For example, many resources like University of Physics video, some people have posted YouTube, so I just give you the link. A lot of things, a lot of videos are here.